Hi and welcome back to another LeetCode practice video. I'm going through the backtracking problems on neetcode.io. LeetCode has this nice list where you can keep track of the problems that you've already solved. There are also video explanations and etc. here, but I'm just going to use it as a checkbox basically to keep track of which problems I've solved. And we looked at a couple of backtracking problems already, so I'm slowly starting to get a hang of it. And I thought the next problem to tackle is the permutation one, which is LeetCode 46. I have tried this before, but some time ago. So I'm going to try this new and hopefully I'll be able to solve it. All right, so we're given an array nums of distinct integers. Return all the possible permutations. You can return the answer in any order. Interesting. Constraints, well, we have at least one element in it, and we'll also have an upper bound, but we don't care for it. Otherwise, space and time complexity would be constant. And all integers and nums are unique. Okay, cool. So here's an example. All permutations of 1, 2, and 3 are, are all the different ways we can arrange these numbers. All of those are permutations. Nice. Here's another example. Of course, a permutation of an array with only one element is basically just, well, a list of that array that contains that array. Okay, so we're using backtracking, which means we're going to use a recursive function. I can tell you that already. And let's do a runtime complexity first. So how many different permutations can you get from n elements? Right, if you have 1, 2, 3, how many do we have? 1, 2, 3, 4, 5, 6. We got 6 different permutations. And if we got 2 elements, how many permutations do we get? Well, 2, right? And if we get 4 elements, how many permutations can we have? Well, the answer is 24. And that is simply n factorial, right? That tells you how many different permutations you can have given n elements. That's what it is. Right, so yes, so well, if you compute all of them, it's going to be n factorial time and space, at least. And so, but I'm going to go with that. I hope we don't have to make it more complicated. And yeah, I mentioned we need a recursive helper function. Otherwise, it wouldn't be backtracking, right? Well, I mean, we could do an iterative implementation, but that would probably break my brain right now. So return result. So we need something to store the result. That is the usual pattern that we can use. And then we have to call the helper, obviously. And with these backtracking problems, you always start with some initial case. And I would say we start at, with the first element, so with an index. We will pick an element, or we will not pick an element. Well, if you think about how the picking of element works, right? So if we have 1, 2, 3, and 4, well, we can pick element 1, or 2, or 3, or 4 as our first element, right? And then in the next step here, what can we pick then? In the next step, we can pick 2, or we could pick 3 or 4. So the order matters. So we need to have some way of remembering which elements we picked, but also in which order we've picked them. And what data structures do we use? I would say we're going to use a list to keep track of which elements we picked in which order. And to optimize things, we're going to use a set to look up if we've already picked an element. And then in our helper function, we actually have to iterate over all of our array elements and check if that element was already picked. If not, we may pick it, right? So we will have, I guess, the permutation and picked well, the picked, I guess, indices. Wait, we have, they are distinct, so we can actually pick the, put the elements themselves in there. Fine. Cool, and we have to have a base case that tells us when we've actually picked all of the elements, right? So that is if length of picked is the length of nums, or we could also say if length of permutations is length of nums, the same thing, right? Picked, if that's the case, we're going to say result dot append. Well, we're going to append a copy of that permutation that we have. Otherwise, what we are going to do is, well, we're going to have a loop for n in nums. So we're actually really iterating in every recursive step over all of these elements. This might change our runtime, by the way. It could be go to 2 to the n. And we're going to check if n in picked well, we can't pick it again. Otherwise, we may choose to pick it or not. And the way we do that with backtracking is we just add it to our permutation list. Append n. But when we backtrack, we pop it out again. And in between, we do our recursive call helper. Now we have to start, well, actually, we don't really need a starting index, right? Because we always iterate over all elements anyways. So the starting index that we had to use in the other backtracking problems, we don't need it here. And so for n in nums is n in picks, we skip over it. And if n not in picked, we will pick it. Do our recursive call with permutation and picked. And we actually have to add it to picked as well. Picked, add n. But we also have to remove it again after this step. Right? Picked, remove n. So, and return result. If we want to do it here, result, well, return helper. We could do it like that. It's not that beautiful, right? You define result outside, so you don't have to pass it in the recursive call. Then you just return it from here. Or maybe we do it like this. I don't know if that's cleaner or not, but it's certainly more consistent. Cool, and yeah, so let's run through an example. Maybe this one. Or maybe that one. This one is too easy. Let's do this one. So we go into a helper, and we have 0 elements picked. We have no permutation. We have no results yet. Now, the length that will return, well, that will be false. So we're going directly into our little loop. And we're iterating now over all of the numbers 1, 2, 3. So none of these numbers are unpicked. So we're going to add this number for maybe the first one would be n. So we pick n. And we add it to our permutation array. And now we go back into the recursion. Now we loop over all of the elements again. We try to pick one, but it's already picked. So we're going to ignore it. Then we try to pick element 2, which is not picked. So we add, and then we go into recursion. We skip over 1 and 2 because they have already been picked. Then we pick 3. And when we come back here, we've reached the length. So we're adding 1, 2, 3 to this thing. Now we unwind the deepest level of our recursion. There's nothing more to do. So we unwind one more. So we still have 1 in our picked. But instead of picking 2, we're now picking 3. And then we go 1 level deeper in the recursion. We skip over 1 that has been picked, but 2 has not been picked. yet. So now we end up with 1, 3, and 2, etc., etc. So I think that is everything, but we have to look at the space complexity now. So we have a clear O of n in every recursive step, clearly. And we also, so how many different ways do we have to do stuff? I still struggle with this. I want to say it's 2 to the power of n. I want to type it, but I can't type it. Oh, there I can type it. Time and, well, we know O of n factorial space. That's what we know. Because that's the maximum number of different combinations we can have. And our approach also guarantees that we don't compute any permutation twice, right? Because we're iterating through the numbers array and not randomly. So the branching factor is actually n. Yeah, it's because the branching factor is n. Like we make one recursive call, and then we branch it out to n calls. And every of those also has n, a branch factor of n. So I think it's 2 to the n. That's what I would think. But why is it 2 to the n? Let's do a calculation where n is equal to 3. Or if n is 1, we will just have 2 calls. But if n is 2, well, we have 2 possibilities for in the first level of the recursion, and we have to times 2. We have to go over 2. Well, in each recursion we have to go over n as well, which is 2. So it's 2 by 2. Now, if we had 3 elements, we would have 3 in the first level of the first level of recursion. Or if you think about it as like a tree, where we with the recursive calls. Why can't I find my my numbers here? This is weird. There it is. Okay. 3 times 3 times 3, right? What if we do n? That means we have n calls, and then in each of them we have another n calls. Then we have another n calls. Okay, I said in the last video I need to do some more research. I guess that remains true. But yeah, it remains true. Well, permutation, results, result. We should run the code. I'm messing things up again because I'm so not used to doing the random complexity analysis after coding. So I didn't even submit this and try it out. Okay, test cases pass. Nice. And that works as well. So what are some of the solutions? Most optimal approach, backtracking. Let's see if we find a random analysis here. Identify the states. The state space, okay. I just want to know if I'm right. Let's go back here. That's the same. n times n factorial. Base complete is n times n factorial. Why? I mean, n times n factorial is the same as n factorial. It's the same. N times n. Okay. Not convinced yet. Another dude without a complexity analysis. Okay, these dudes say it's factorial time as well. But is it though? We're picking n elements, and in every step we're running over n elements. So our recursion depth is n, and at each step we can make n computations. Because of this checking, you know, if it's in picked or not, we have to go over all of them. So it's definitely not factorial time. No, it would be factorial time if we have less and less elements to go over to pick from, but we don't. We run over all of them every single time, don't we? And it's not n times n because that would be n squared. N, is it n to the power of n maybe? Maybe it's that. I know I'm not helpful. Let's see the discussion here. Don't people normally discuss these things? Okay, this dude made a video. So it's doing, but it's not, yeah, I don't get it. So the analysis is not that great. Maybe you should look that up and don't take my word for it.